Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 1, the real start of the course, if you will. Before we had a prologue with lecture 0 showing you a bit the course content, and then a practical lecture 0.1, which was a bit like looking to SSH and Unix. But today we really want to basically kickstart the course with an understanding of high performance computing. And this is sort of an impossible task to have one lecture to give you a grand overview. This has been now growing tremendously in the last 20 years, high performance computing, from a more niche, you would say, in scientific engineering fields to much more mainstream usage of HPC. And we will make the point of it in the course. However, I try to bring you the most important topics to get a overview, and then also will refer, of course, here and there to lectures where we'll have deeper material in different areas like distributed memory, shared memory, but also deep learning, distributed deep learning, and so forth. So, however, before we go into the topics of high performance computing itself, let us review what we had the last time, because it's sort of really essential to understand that we had this SSH, and this is still the modus operandi to use basically the most systems that you have around the world. Many of them have more and more easier access paradigms, but if you need access, let's say on a very low level basis, SSH is usually always supported. Hence, we did this as a sort of warm-up for the course. Both Unix and SSH are usually taught rather in operating systems courses, or let's say in other basic courses. So here I just brought with the last lecture, hopefully you a little bit, the idea how that generally works. And when you want to access, let's say, as we had the last time, the deep system, this test cluster we're going to use in the course, or our own system here in Iceland, Elia, then the way how you use it with the SSH would be usually via so-called SSH keys, right? Or as the people refer to it as public-private key pair, right? But you basically, this is the more official name if you want. If you are in a center, a European supercomputing center, you would always call them SSH keys. And of course, I could told you much more about it, but we keep it to the essence to understand how to log into the systems, what you should also do during the course. So if you remember, we used one of the MobiX term SSH client, for instance, for those that are on the Windows, let's say, operating system. For others, for instance, Mac users in the course, you can also use, of course, then the normal client that you have in Mac. Usually there's an SSH already available via the command line. And of course, this goes as well with all the Linux derivatives that you have, whatever brand you are using. However, we learned also that there are initially kind of setups to prepare in order to basically connect to such a system. And this is a little bit explained with this graphic here that should be giving you a quite overview without going into too deep details what the secure shell protocol is and so on. So you have your host, and in order to access in some point in time in the future the HPC system, it's essential that you create first this interesting private public key pair. And our first assignment, one of the first, let's say, tasks is really to do that. And you will see it's not a big deal to do this. However, there are a couple of things that you have to understand, and that is first and most notably perhaps that the private key remains always on your system. Hence, don't send that around in emails, don't transfer this to many different systems. Usually we say the private key stays at your host, at where you created it. And as the name suggests, the public key is completely different. So the public key is something you can share with many different administrators. You can give it to the deep test cluster administrator. You can give it to the Elia administrator, because the public key is something which they need in order to prepare the system. So they will give you a username usually on these different systems. If you remember, what we had the last time was that it was Riedel 1 here in the Jülich hemisphere in Germany in the deep test cluster, and there was Morris here in Iceland. And this is the first ingredient you have as a, let's say, important element how to access such a system. However, the public key pair, public-private key pair now is the key to really then access it. And with this, you also need, of course, a host name in order to basically access it. And this is what the administrators will do. They will make, the username accessible with a certain public key, where you're supposed to have the private key. That means every time you go to some system and there's a public key from you already uploaded, or you basically gave it to administrators, they upload it for you. It is expected from you that you have the matching private key, right? Not any private key, the matching private key. And then you can see basically how that works. You essentially want to contact such a system, and on your host you have, of course, the private and public key. Sometimes even it's in a key store, as I has demonstrated last time, so you have to give probably also a password, at least the first time you use it in a session. And then the public key is already uploaded on the HPC system. So when you establish a connection, the public key will be used for the instance of these connections and will check, do you have really this kind of private key available? Hence, when you connect to such a system, like in MobileXterm, you have usually also this link, so this private key. And this is then the second ingredient. And of course, the final ingredient is the host name, right? So we want to compute remote. And this is an important takeaway message. We don't use Eclipse with Java on our own system or something. We don't program C here on our own system. Basically, the idea is always go to the remote site and then use remotely this HPC machine. That also means you don't need any more a GPU in your desktop machine or in your laptop, because we have seen in some of the examples from the joint undertaking, for instance, from all these different HPC systems, but also the one from Jülich, we have many thousands available. So there's no point of having a, as we call, thick client anymore, because you are basically relatively fine to just use a private key, a private public key pair in order to connect to these remote systems. And the remote systems are very powerful. However, they have, of course, one element which is sometimes a bit a hassle for people, and this is a Unix operating system, or let's say any Linux derivative. So Unix skills in HPC are also important. Again, a topic for operating systems and other courses in the university. So I also kept it to the very brief elements of it. So we did something like host name. This is important to understand. Oh, I'm really remote, right? So when I logged into deep, using, for instance, here this deep.fz-jülich.de and then the username with the matching keys, I was on such a system and could check it also with some Unix command cost that is known as hostname -r, giving you here also the location somewhere in Germany under the name deep. Or if we went to with a complete different username to Elia here in the ERHPC in Iceland with the hostname -r, we see also the domain of the university here. Hence, Unix skills are sort of important. There is a momentum with many AI users and others, let's say, around data science to use more Jupyter notebooks. We will come to this in one of the later lectures when we talk about deep learning, machine learning, and so forth. But this is really the key essence in the beginning of the course to handle this, because if you want to work in the area of HPC, you usually are required to have usually SSH and Unix skills, at least to a very basic degree. A final point, because it's also very important, is the module system here. So module load Python was an element where we said, okay, there are different modules already pre-installed, applications, many different elements. Some of them we will learn in the course, PyTorch and so on for deep learning, for instance, or basically NetCDF or HDF, like parallel data formats, etc., etc. But this is something where administrators have already pre-installed elements, and we will come to this again and again in the course. So I showed you just a little bit how you handle the module system, how you can see which modules are available by using module avail. So I spent a lot of time here because I think the SSH key point is always something which is not completely understood by everyone, and also the remote execution is not completely understood by everyone. That is, of course, something which makes HPC a bit different, maybe from other subjects in the university where you do everything on your own laptop and assignments on your own laptop. Here we will go remote. But when you learn and master this, this is my final statement, you can also see that your HPC JU undertaking machines, you're ready to use not only the eHPC from our Icelandic HPC community clusters or the desk cluster in Jülich, you also basically have the basic skill set to also use the systems in the union with your HPC joint undertaking machines. So let's go ahead and think about high performance computing as a whole. So we see it's sort of an introduction lecture where I will be perhaps a little bit sometimes be still from 10,000 feet perspective looking on some topics, but then give you already some examples to concrete lectures where we dive into the details. So high performance computing means, of course, we want to understand a bit the basic building blocks. Is it just about hardware, or is it perhaps also about many other aspects? And I think that's an important part to say, including applications, which I would like to elaborate on, but also different other key elements to it, like scientific visualizations, for instance. Then the whole idea of performance, why we call high HPC machines partly supercomputers, and what are architectures that are a little bit, important to understand. Also here we will go in some of the other directions later in the course. But we start with a general understanding of multi-core processors and parallel computing. Hence, we have to talk a little bit about shared memory and distributed memory programming and also the architectures of the system, while, of course, lecture 2, 3 are all about it. So we will also lecture 4 then with OpenMP, learn about shared memory. But before that, we start really with distributed memory to really understand why I can scale up to many different nodes, why I do message exchanges, and so on. Finally, just some pointers to hybrid architectures, of course, which we see more dominant today, and also the enormous programming complexity that we are facing now in HPC, because we have not only, let's say, MPI across the nodes, shared memory, and OpenMP within the node, we have also accelerators these days that are attached to the nodes. So there's like a three-way programming, if you want, right? And this makes it quite complex. This will be the first part. In the second part, we again take a bigger look, and this is about HPC ecosystems at all. For you, it's important to understand in our practical lecture 1.1, we also will then go directly in more examples of the software environment. So in a way, you have already learned one with the module system in practical lecture 0.1. But then we quickly go also thinking about, software environments, then the technologies we have coming up in the last 10 years, really with significant speed, many core GPUs. We have a whole lecture on this, but of course we give you some sneak previews. Also why it's so essential today, why we need GPUs for machine deep learning, which is really then able to tackle big data at scale. And then also a little bit which might be more the community aspect in it of our Icelandic National Competence Centers. Again, why making the connection also to applications is so important in this HPC National Competence Center with so-called simulation and data labs. And I will make the case for it also because we will see with a modular supercomputing architecture, you learned a little bit already. The supercomputing co-design with applications is a key point, because these systems are always a cutting edge available, right? So this is still, if you want a little bit of research in a way, how you build these systems. In the moment in Germany, we built the exascale system of Europe called Jupiter. And this is something which goes back to quite a modular supercomputing architecture research in the last 10 years for different deep projects, and now manifesting in this first European exascale system that we see in Germany, also co-funded, of course, by the EuroHPC joint undertaking. At the end, just some, let's say, related work elements in HPC. On the one hand, we would say large-scale infrastructures is something what is very important for us. So it's phrase had a certain history in HPC we should look at, but also looking into the future when we think about what is also quantum computing in context is a very important part in HPC. So when you want quantum computing is, of course, in a way, a discipline of its own, but it's really closely related to HPC, and in many cases, somehow very closely combined with HPC machine, because what we see is in the moment that the quantum computers are still not really general computers, so to speak. They are rather accelerators of a certain type. So fasten your seatbelt for the first real lecture on HPC, and afterwards you really have the latest developments in parallel processing and high performance computing. Again, we look into architectures of this high performance computers, clusters, supercomputers. So you will be understanding, these, and also how to basically create them from scratch when you have then different node cards up to racks and so on. We go a little bit into the complex aspects of parallel programming already to warm you up for our upcoming lecture 2, 3, and 4. So parallelization is a key that also will give us, then, of course, indirect insights in later lectures of domain decomposition. So coming to the high-performance computing basics. So this is quite an interesting term because it also redirects directly to supercomputer. So these are very much close to each other, supercomputer. Now questions today, of course, remain at what point in time you would say it's a HPC machine, how many GPUs have to be in a machine to be rather a desktop, variant of having 4 GPUs maybe in a very special system you can still put under your desk. Provided by NVIDIA solutions, for instance, but also the idea of a supercomputer, so where that starts. And I think one of the general themes you see in supercomputing is that we are the Formula One, right, of computing in one respect. We always use the latest, greatest of NVIDIA GPUs to create the modern and more, let's say, powerful supercomputers almost on a half-a-year basis. I come to this. It's called Top 500. So where you then have a list of all the top supercomputers in the world that are known. Of course, there would be some computers that maybe don't submit to the list and might be somewhere. Potentially even in military systems, we don't know, it's classified, whatever. But still, this is something where we're really at the cutting edge of processing. And another one is often also that HPC is characterized, and I was making the point before in the prologue and before, that we have this interconnect between the different nodes. You will have questions, what exactly is Morris now? And you are referring to nodes. And I will come to this in the next couple of lectures where we then also learn this. But think about that you really use these nodes, and that's why I make an emphasis here on the interconnect. Really is lots of message exchanges. This will come in the next couple of lectures. Even deep learning is using the interconnect a lot. And we are not so high throughput computing as I was alluding to before. And then when you think about high performance computing, what it entails is really not just hardware, right? And this is another aha effect I see often in students. So everybody thinks just HPC means, well, this, right, that you see here on the picture, lots of racks in a long corridor, putting lots of hardware in. So there are lots of theoretical elements. We will learn many in them in the course. Speed up, actually limits of speed up, numerical laws based on known physical laws, multi-core versus many-core. You have network interconnects. You all have to store some data somewhere. So this will be also one facet in some of the lectures. So cutting-edge technology plays in, not only theory. And then all the architectures, you would say, well, HPC machine is a HPC machine. It's absolutely not the case. Some use, let's say, accelerators from NVIDIA, and you have here good examples from Lumi. That is actually, if you look closely, what it entails to have, let's say, the GPUs. You see, it has an AMD Instinct card set of system with GPUs, being not from NVIDIA. So you have heterogeneity in the hardware that constitutes the architecture. We will learn about shared memory distributed in a moment, but still take away the message that the architectures can be very different. Although they're all maybe HPC machines, they're all here and there partly called supercomputers, but there's so much variety in technology, architecture, and so on, that then, of course, gives us also the fourth ingredient, which is a wild, you would say, jungle of software, right? The module environment I showed you already in the last practical lecture was pointing to it. Lots of libraries and things, but also applications. There are different applications. We will learn a few today in this lecture, but then also during the course, especially with the CFD, special computational fluid dynamics, later by Reza, you will see even one application domain like CFD can have many facets. So hence, applications, libraries plays a big role. And then we will learn also in the next practical lecture that there's lots of this system, let's say, ecosystem, or what we learned already with the module system. We need schedulers to have multi-user access and also monitoring the system when you have large systems like 3,000 GPUs for 4,000 GPUs in the system, you must be able to monitor the system in case of errors, failures, and so on. So practical is, of course, here for us also, and in your, let's say, generation, is that you can always access your HPC systems. That's an important part that we here and there will also give you as a point. So these systems are not accessible. So even companies, when you're ready here with university studies, can apply it in order to get HPC time. And we come back to this during the whole course, and also with the eHPC workshops we run in parallel, and would encourage you to attend. We'll also make cases for it. Just to revisit what I had in the prologue, so I don't spend much time of it, I think everybody has now understood that the network interconnect in HPC systems is sort of very important. It might be not so important for teaching clusters. You will notice our U-turn is a little bit different. Still, we consider HPC system because all the system software is on it. Modules, we schedule with Slurm, we monitor it, Ganglia, and so on. So essentially, of course, we're talking a bit different if you have a cutting-edge supercomputer, right, where scientists use it maybe at full scale to solve cancer or other applications that you already got from, I hope, the praise video from the last or from the prologue lecture as an appetizer. And this is, of course, an important part compared to maybe teaching clusters, which are a bit lower in performance and, of course, have just a couple of GPUs, but still fulfill its purpose of being a teaching cluster. Differentiates also then quite easily to the HTC world, where you basically have the interconnect not so relevant. You would solve a problem in parallel, not interacting a lot, so the interconnect is not so important. And I took this much more with MapReduce and other concepts in the cloud computing and big data course. So not for here, but some of you are from this course, going now into the HPC course. So here you have the connection. In HPC, what we do much more is looking more into parallel computing, right? So parallel in a more lower level sense, right? And this means whenever we want to basically solve a problem in a cooperative way, and you see here basically the idea now mapping from the nodes that you have or the different CPUs that are available here. We have different processes that live at the same time in parallel, and we want to make use of it, right? Hence, this is a basic for parallel computing. We have not only one or two, core setups that we have in a laptop that you basically see these days have quite some number of cores. Here we talk a bit really scaling up then much more than just maybe 5 processors, right? It's just more for an illustration here. Hence, parallel processing is now the idea of combining these different processes in the best performance possible to solve one problem in a cooperative way. And we will learn in this again and again in the next couple of lectures coming. And the high performance in this means that we have their benchmarks ranking the best 500 computers or supercomputers if you want. And they should be also then very much capable of enabling this parallel processing because this benchmark needs it. We go more into this on Parallelization Fundamentals, the performance term, but means now high performance. In some theories also in the lecture 3. So I keep it as there, rather give you an impact in applications, and with this automatically the nice connections to scientific visualizations, because HPC simulations can be quite abstract. And you see here quite nice examples, of an airplane flying alone. This turbine is already a very interesting problem in engineering and challenge in engineering, of course. And if you see there what that is a simulation over time, right, of this one little turbine, and not speak of the whole airplane, right? There's turbulence to simulate, and you see really that there, Bernoulli's principles coming. There's domain decomposition with this sort of mesh you see here, which is also a term we will come to later on. But it can be complex. Hence, you want to do often this physical, let's say, process to be understood with visualizations. We come back to this again and again. And the same is actually true for AI. You would say it's also quite complex. You have your land cover from satellite images where you want to understand the land cover and classify it with AI. But there you see suddenly that, of course, the satellite looks a little bit into the earth with different spectrums or spectral channels really of light and so on. So we have rather a block instead of just, let's say, the surface. We come to these topics and also to these many often in the course. Here's another example of the Eyjafjallajökull volcano and the eruption, if you remember, and the plum has taken out lots of the kind of airplanes over Europe. And here you know why, because essentially lots of that was affecting Europe. Hence, with visualizations, it says, as it is often named, right? It's more powerful a visualization than 1,000 words. Also, when you understand now parallelization, you want to have a race car in parallel simulated. You will put it in mesh. You want in parallel give it the processing to this very complex airplane to many different processes using a mesh. When you want to simulate maybe the ocean, basically that we have around Iceland, you would basically have here a domain decomposition. We come to this in lecture 3, which is again a mesh, and then would solve this in a collaborative way, the wave propagation perhaps here, and so on and so on. So here you see a blood pump, another element of a physical process then interacting with the environment and the blood. And also the engineering of this is, of course, understanding stress on blood vessels and so on. Then you have particle simulations where you rather talk about points, but these points have, basically lots of particle interactions, as we call it, long range, short range. And this is also something where lots of computational capacity is required. But having visualizations enables us to better understand these, let's say, different data types and also the different laws of physics which might be affected. Coming now to the top 500 list. So again, this is more about having a benchmark that is listing these systems. So some argue it's not really, let's say, application specifically performance, but we see here also now in the top 500 list, and the list is of course here provided in one of the references, that there's a top 10 in the list, and you see that the US research laboratories have already exascale systems. This is Lawrence Livermore, this is Oak Ridge, and also Argonne National Laboratories. So these are really big, large US facilities with lots of money, really fueled with very powerful systems today. And also you see a little bit then the EuroHPC joint undertaking still being in the top 10 with Lumi in Finland and Leonardo in Italy. Then, of course, down in the list is one of those Jülich systems. I was giving you the example last times already with older Ampere 100 cards from NVIDIA, because the reasoning is that Jülich is, of course, preparing a little bit for the Jupiter system now with Grace Hopper cards, NVIDIA cutting-edge technology to become the first exascale system in the world. In Europe. In the world, we have seen that already here with US research laboratories. An interesting thing with the top 500 list that is given out every half a year is also that you can look into many different statistics of the list. So this is one interesting one, vendor system share, and how this changed over time. Lenovo, one of the big provider, Eviden was actually Atos before, and of course NVIDIA, some that you know. But also then into technologies, this is possible to look at. So you see here the different, let's say, generations really of NVIDIA cards, how they basically are mapped to the top 500 systems. This is the Ampere line, the Volta line, for instance. And then the H is now the new ones, the Grace Hopper or Hopper cards, which are now interesting, all NVIDIA cards. You see quite the market dominance of NVIDIA, but also the AMD Instinct, as we were suggesting also in Lumi, is there present. So it's not all NVIDIA, but you see clearly that NVIDIA has here some dominance. So the way how it is computing this top 500 I was alluding to is a little bit sometimes in critics. It's quite linear equations that are solved, a dense system over time. And this is not really how several applications work, right? So there is more and more realistic application benchmark suits that we also use, for instance, in Jülich, Uber benchmark suits, and so there are HPC challenge benchmarks, which are much more application specific. So even if you have a top 500 systems and you're higher in the list, chances are that the application's running better on a system which is a bit lower in the list, just because the application may not need exactly what this made it to the super duper top 500 system. Hence, the applications are important. And that's also the reasoning why so much money is put into the supercomputers today, because the parallel computing bears the potential to solve many problems. And with this, we see also that, of course, more and more there's a requirement to support more different users, and you have learned how we do this also with different modular supercomputing system approaches. Hence, this can be maybe better to support the applications, because in the long run, it's that what we want to do. To be just, let's say, number one in top 500 is, of course, a good political statement, and say, well, US has definitely the lead, but the applications are equally important in how you use and make use of the system. You see also in the area of artificial intelligence, there's now MLPerf for benchmarking become available. We will talk about this more also later in the course when we have a better understanding what really machine learning is. But you see here a little bit the areas of, with image classification, speech recognition, natural language processing, and so on. And so on. These are all topics which are heavily AI related. And there's also more or less a change now that we have seen in the last 10 years of using HPC. More and more AI, machine learning, and deep learning is entering. I talk about this more when we talk about GPUs in the second part today. But let us come still to some basic terminologies, if you want. So multi-core CPU process is something what you probably almost all know, or should given, from the 101 computer science course in our university, or even in operating systems again. But here you have, of course, a multi-core system, different cache hierarchies, like it is suggested here on the right side. And here we usually think about cores as high single thread performance. So these are really number crunches. They have a very high clock frequency. And there's a sort of limit to it. So you cannot make the heartbeat, as it is called sometimes, right? This kinds of hertz higher and higher and higher, because then the chip will overheat and will just give errors and have a problem. So hence, here the idea then that we discussed in the second part is then having this many core processors. But this is an important facet for you to understand that this is a multi-core CPU processors. They are still very relevant. There are applications that require these CPUs instead of GPUs. And we will see in the course how that materializes. Hence, let us talk now in the remaining time a bit about dominant architectures, now bringing these all together, this kind of CPUs on different cards and racks and so on. The way how you would see such a system is essentially that you have these two dominant traditional types, so shared memory computers and distributed memory computers. But the reality is, of course, today that you have basically both in practice. You have hybrid systems that are there and that can be combined, of course. Of course, on top of this, we have now the accelerators, so NVIDIA GPU chips and so on as well. Hence, the programming models is basically the idea how you rather see that instead of shared, memory or distributed memory architectures. So let's dive into this a bit more with shared memory computers. And also here, I just give you an initial view, because we will have in the assignment in our lecture 4 also much more details on shared memory. Here, the standard to operate on is OpenMP. It's a standard for programming shared memory. And here you would have one node, for instance, with shared memory and many different threads you kickstart in order to solve one problem in a collaborative way. And you would have not message exchanges. You rather, as the name suggests, you communicate via the shared memory. So you put variables into the shared memory and you read them from other threads and so on. Hence, we have synchronization problems, critical areas where lost updates are, and so forth. And the different varieties, unified memory access and cache coherent non-uniform memory access, which is essentially distributed memory, but we don't see that because they're so-called cache coherence protocols that avoid this. But long story short, every task can basically access a memory, making it relatively easy to program. And that's why you see the MPI, the OpenMP compiler directives that mark those parallel regions like loops, for instance, are usually relatively easy to understand. And this is, of course, available in many different languages, and usually it's done a lot in C, C++, and Fortran, because many of the scientific applications are in that. However, to differentiate it from distributed memory, which we will have later, think about that the threads that you see here are rather lightweight processes, right? They're not really full processes as we learn in this kind of typical distributed memory programming. Just shortly to show you this UMA, as they call the flat memory model. Here you see the different processors we discussed with all the different level of caches have really access to the memory directly, right? So this is an important facet when we want to do shared memory. The cache makes it very fast to read and have this access to these different memories. But it's also, as you can remember already, to a 4-core system here or so, it's very let's say, limited, because you just have a shared memory access with a couple of cores bind to this memory. Now you see here a sort of system called CC-NUMA, which effectively is a bit like a distributed memory system, but it has this cache coherency procedure in it. So it still feels for all the processors that you have here as if you have your shared memory and local memory. Hence, you would still program it with shared memory, and it is still, as we would maybe call it, a single address space, right? So you don't have to care about this, essentially, that it's distributed as a developer, and with it makes us aware of it, and it would extend a little bit, let's say, the possibilities that we can have a shared memory, but again, it's very limited. And why I'm saying this limited thing is, of course, when you now go to these large systems that we have seen here in the picture, now I have rack after rack after rack after rack after rack, and et cetera, et cetera. So here we talk about that this looks much more like this, right? You have different nodes with processors, memory on its own distributed, and the other processor cannot access the memory of the other processor, so, or of the other processors in the node. Hence, you always have to go over the network interconnect. That's why we say the network interconnect is so important, to exchange messages, to put this into the memory space of another processor to work on, and then basically work on other results from others to do some result. Or if you want, go to send the message, work on it, send it back, done. So here you see already something which we will now continue in the course, also in lecture 2 and lecture 3. It's clear that you maybe don't understand all at once, but here you can see directly that you have to communicate in order to get information, receive information, or send information to others. You cannot just put it in memory and done, right? No one else can access the memory. So you basically have to have this message interaction. And we use the MPI standard for it. It's very well known, the message passing interface, as the name suggests, message passing a lot in parallel. And the beauty is it is very scalable, right? So even if I suggest only 5 processes here that are interacting with each other, here we go up to thousands of processes over thousands of nodes. And I will make the case for it when we come to lecture 2 and 3. This is the introduction, so we cannot do everything in detail. There are also different implementation of this standard, for instance, OpenMPI, but there's also Parallelization MPI and different others that have implemented this. And we're going to use that in the course for one of the assignments. Hence, if you have a real computer these days, which is really filling the hall, you have a picture much more like this. And even this picture you have to augment now with having here and there accelerators along the way. So here we talk about the processors having their own shared memory, and then you would have another set of processors with their own shared memory. But if they want to collaborate or solve a problem in a collaborative way, we have to use a communication network, which could be InfiniBand or another, let's say, type of interconnect where you have this message exchanges. So what you can do is essentially in this hybrid computing today do shared memory programming inside a node here and here and here. But every time you want to communicate and work together with another node, you have to use MPI. So you would use distributed memory programming across the nodes, but shared memory programming within the nodes. And then on top of it, would also consider GPU accelerators. But this would be all too much at once to teach. Hence, we will not going so much in programming these hybrid systems. As I was saying here, MPI for parallelization is probably the most dominant programming paradigm now in general. But of course, the GPUs with their CUDA and libraries, which are now leveraging many cores that we will learn in the second part of the course, is also now getting more dominant, right? So it's really increasing in many application domains as well. So in this sense, We will learn several challenges, also what it means to program in parallel, and in both actually, in distributed memory and in shared memory programming. But if you understand this and you're also well prepared to, let's say, have the HPC systems in the union from your HPC programmed with some nice applications, or understanding application codes which are based on MPI and OpenMP. So to summarize a bit on the supercomputers that you have seen, the different application requirements to one supercomputer, you see that a little bit here, and also how we see quantum computing yet as another module here. I encourage you to look at this video, and we will continue then with the second part of the course with the HPC ecosystem technologies in a couple of minutes. So talk to you then.